Hello all, so in this video we're going to learn about differential equations. So we're going to talk about what they are, and then we'll solve some initial value problems, which this video is all stuff you've seen before. Just putting some new vocabulary onto things. So, differential equations, what is it? It is any equation which contains derivatives. You've seen it before, dy dx equals x squared. So either ordinary derivatives or partial derivatives. We haven't learned partial derivatives. You'll learn those in college. So differential equations are useful for modeling and simulating phenomena and understanding how they operate. For example, Newton's laws of motion, Newton's laws of cooling. We're going to talk about growth and decay problems, so like population growth or bacteria growth or decay. That's what we're going to talk about. Also, like radioactive decay can be modeled with differential equations. All kinds of things, really. Oh, spring mass systems. Really all kinds of things. So that's what they are. That's some useful aspects of them. And now we'll talk about some initial value problems, which these are review. We've seen things like this before. So if dy dx equals x squared plus 1, what's y? This first example, we just need to integrate both sides and multiply by dx. So here we'll do, so the integral of dy dx is y. The integral of x squared plus 1 is 1/3 x cubed plus x plus c. For this one, we integrate both sides. We end up with y equals 1/3 times cosine. Negative cosine. So negative 1/3 cosine of 3x. Because the derivative of negative cosine is sine. This one is one that you will have to just know. But this is, if we integrate both sides, the integral of 1/1 plus x squared is the inverse tangent. Sometimes we denote that as arctan. The arctangent of x plus c. Or you might see this as y equals the inverse tangent like this. These mean the same thing. That's just a common derivative. The derivative of inverse tangent is 1/1 plus x squared. And lastly, we're going to review u substitution with this one. Alright, just erase to give myself some space. So, derivative dy dx equals x times the square root of x squared minus 1. We're going to set u equal to x squared minus 1, because then du equals 2x dx. Alright. So we can separate this. We'll say dy is equal to x square root of x squared minus 1 dx. We integrate both sides. This becomes y equals, alright, now time for our u substitution. Alright, under the square root is easy. That becomes the square root of u. And we want to put in du, which means we have to replace with like a 2x. So we want this to be du. But notice here that we only have an x, but we need to replace a 2x with du. So we'll counter that by multiplying by 1/2 up here. Alright, then this is the integral of this. So this means that y equals, let's see, square root of u becomes u to the, so this was to the 1/2, now it's to the 3/2, multiply by 2/3, so 1/2 times 2/3 plus c. Alright, so we'll simplify this. So this is y equals 1/2 times 2/3 is 1/3 times x squared. Here, I need some more room. Okay, this is y equals 1/3 times x squared minus 1 to the 3/2 plus c. And there, we solved for y for 4 different differential equations, which is all stuff you've seen before. So let's go ahead and move on down here. So this is some review of some velocity, acceleration, position. So the velocity of a particle in the number line is modeled by the function v of t equals 6t minus 4, and it's known that at t equals 0, so at the starting time, the particle is at position 4. Find the original position function for this model. So to do that, we're going to use this velocity function v of t to find our general position function by integrating it. So that means that s of t is the integral of this v of t. If s of t is a position function, so this is the integral of 6t, which is 3t squared, minus 4t plus c. This is where we're going to use this initial condition. So our initial condition is t of 0 equals 4, which means s of 0 equals 4. So we're going to use that to solve for c. So 4 equals s of 0 equals 3 times 0 squared minus 4 times 0 plus c. Alright, so that just means 4 equals c. So our position function is s of t equals 3t squared minus 4t plus c. Oh, sorry. Whew. Plus 4. Because we found c. c is 4. Alright. And that is the position function for this model. Example 2. Find the particular solution to the equation dy dx equals e to the x minus 6x squared, whose graph passes through the point 1, 0. Okay, particular solution means find y. Alright, so we got dy dx equals e to the x minus 6x squared. So we integrate both sides here, and I'll separate the dy on one side equals, so multiply by dx, e to the x minus 6x squared dx. Now we can integrate both sides. So this is y equals, the integral of e to the x is e to the x. The integral of 6x squared is x cubed, 2x cubed plus c. And now this is where our initial condition comes in. So this means when x is 1, y is 0. So we'll go ahead and plug that in. So this is going to be our initial condition. So y is 0 when x is 1. So 0 equals e to the 1, because we're going to plug in 1 for every x, minus 2 times 1 cubed plus c. So that means 0 equals e to the 1, which is just e, minus 2, because 1 cubed is still just 1. So our particular solution is y equals, oh, I'm so sorry. We missed something here. Plus c, which means that c is equal to 2 minus e. Okay, now our particular solution. Y equals e to the x minus 2x cubed plus c, which is 2 minus e. And that is our particular solution. Which means if I plug this y in, if I derive this and then plug it in, I'll get e to the x minus 6x squared. Alright, so let's keep going. Got one more for you. So example 3, a car starts from rest at t equals 0 and accelerates at negative 0.6 t plus 4 meters per second squared from 0 to 12. How long does it take for the car to go 100 meters? Alright, so we know the acceleration function, negative 0.6 t plus 4. So let's find the velocity function. Let's see. So the velocity function is the integral of the acceleration function, which is, let's see, this will be t squared. This will be negative 0.3 plus 4t plus c. Okay, now to find c, we need to know some sort of initial condition. That's given right in the beginning. So car starts from rest. That's the key here. That means they're starting at 0 velocity. So at time equals 0, we have 0 velocity. So time equals 0, we have 0 velocity because we're starting from rest. So that means, let's see, when we plug in 0 for t, this whole thing should equal 0. Which means that 0 equals, if we plug in 0 for t, this first term is 0, the second term is 0, so 0 equals c. Which just means that c is 0. Okay, so that means our velocity function equals negative 0.3t squared plus 4t. Alright, now we know how to find the position function, which is the integral of the velocity function. So s of t equals, let's see, this is going to be t cubed, which would mean this would have to be negative 0.1 t cubed plus 2t squared plus c. Alright, now, again, same thing, initial condition. The car is starting from rest at t equals 0, which means that its initial position is 0 at time equals 0. So again, our initial condition here is 0, 0. So to find c, we plug in 0 for s of t, and then plug in 0 for all the t's, but notice this first term is 0, and the second term is also 0, so 0 is c again. Which means our position function equals negative 0.1 t cubed plus 2t squared. Now, our question is, how long does it take the car to go 100 meters? Remember that s of t is the distance traveled. So we'll plug in 100 there, and then we're going to look for t. So 100 equals negative 0.1 t cubed plus 2t squared, which means that 0 equals negative 0.1 t cubed plus 2t squared minus 100. So there is a formula, like the quadratic formula, like the cubic root formula. You can use that if you wish. Fun story about that, that's actually one of the origins of complex numbers, is the discovery of the cubic root function. Or the cubic root, the cubic root function. So if you want to find that formula and use it, feel free. Another way, you could graph it, find where it crosses the x-axis. This is 0.1 t cubed. Yeah. So if you can graph it, find where it crosses the x-axis, you'll find that this crosses the axis at t equals 10 seconds. Which means the car takes 10 seconds to go 100 meters with this acceleration function. So that's it for the initial value problems, and that's it for this video.